Hi, I'm Hyungjin Chung, a PhD student at KAIST. Today I'll be sharing my recent works on solving biomedical imaging inverse problems through the lens of diffusion models. So, as many of you might know already, diffusion models stand at the core of generative models nowadays. Starting with DALL-E 2 and up to Stable Diffusion, diffusion models are considered the state-of-the-art on modern generative modeling, capable of generating high-quality images like the image that you are seeing right now. To start with the very basics of generative modeling, let us revisit the whole purpose of generative modeling. In this model, the holy grail is to learn the probability distribution p theta of x, which, without loss of generality, can be decomposed as the exponential of the energy components f and the normalizing constant z. Now, in most interesting real-world cases, x is very high-dimensional and spans a very large space, making the normalization constant impossible to compute. One way to circumvent computing the normalization constant is to instead learn the Stein score function, which is defined as the gradient of the log density. This is because when we take the derivative with respect to x, the normalization constant now vanishes, leaving us only with the energy term. To build some intuition, let us assume that our probability density is given as a mixture of two Gaussians, as shown on the left. Now, what would the score function look like? It will in fact look like the gradient vector field shown on the right, with the vector fields pointing towards the high-density modes of the distribution. Now, our task would be to learn this vector field given some empirical samples given in the middle. How would we learn this? We could do this by the so-called score matching, which tries to minimize the Fisher divergence between the ground truth score and the output of our neural network s theta of x. However, as we do not have access to the ground truth score, we can use the following theorem that states that denoising score matching is equivalent to explicit score matching. Now, when using Gaussian perturbations for the noising kernel, denoising score matching actually becomes fully tractable. To inspect why this is so in detail, let us define the perturbation kernel as some Gaussian kernel with standard deviation star sigma. Then by definition, we can write down the gradient of the log perturbation kernel as follows. Plugging in, we arrive at the conclusion that since x tilde minus x is the noise component added to x, denoising score matching predicts this noise component, and hence this is equivalent to training a residual denoiser up to some constant. Now, once the score model is trained to optimality, we can use, for example, gradient-based MCMC schemes such as Langevin dynamics to sample from the distribution by plugging in our neural network in the place of gradient of log px. Oh, so this is a typo, it should be gradient of log px. We see that starting from random noise, the samples will be denoised, or in other words, pushed towards the high-density modes of the distribution as we perform iterative Langevin dynamics. To sum up, given the empirical data samples at hand, we can perform score matching to estimate the score function with the neural network. Then we can perform MCMC steps such as Langevin dynamics to draw new samples from the distribution. In practice, in order to boost performance and avoid pathological behavior, one trains a multi-level residual denoiser. Then, at sampling time, we start from a Gaussian noise with very high noise level, and slowly anneal the process with lower and lower noise levels to draw new samples. Intuitively, the generation steps looks like the figure on the bottom, where our score function gradually denoises a given image by producing a less and less noisy images at each step. Interestingly, in the continuous limit, this annealing process can be described with the noising forward stochastic differential equation and the generative reverse stochastic differential equation, where the score function governs the drift function of the reverse SD. So the score function really governs the denoising process or the actual sampling process of this generative model. Okay, so I think that was enough ranting about what diffusion models are. But we still have not talked about how these are relevant to inverse problems, what we are aiming to solve here, and especially inverse problems that arise in biomedical imaging. Let us now dive into the meat of the talk. So what are inverse problems? Mathematically, inverse problems are problems of recovering a clean image X that are obtained through some integral imaging system A, contaminated with measurement noise eta to become Y. For example, the image that you are seeing here is the case where the imaging system induces blur, and there is additive Gaussian noise in the system. Now, since all the inverse problems are inherently ill-posed, there exist infinitely many solutions that are feasible for X. But for a solution to be good, it is not enough just to be feasible. It has to look realistic or look like a sample that is actually derived from the prior distribution. That's where the prior of the data distribution comes in. The English word for the prior is how should the image look like? Representative inverse problems that arise in imaging systems are in painting, deblurring, and in the context of medical imaging, there is also compressed sensing MRI. Notably, although the measurement processes are completely different, mathematically, all these systems can be cast into the same form of y equals ax, which is a linear system. To go into a little bit more detail about compressed sensing MRI, the measurement is usually given as follows. You have your ground truth image X, and you typically have multiple receiver coils that are placed around the body. According to the location of the coils, sensitivity maps are multiplied element-wise. Then, the measurement is actually acquired in the so-called k-space, or the Fourier space, such that the measurement will be emulated if you take the Fourier transform of each coil measurements. Now, to accelerate the scan, the k-space will be subsampled, meaning out of the whole space, only the red dotted points will be sampled, making aliasing artifacts that one has to remove. Another relevant case in biomedical imaging would be computed tomography, where the measurement is now obtained through the so-called radon transform, where each column of the measurement is obtained through shooting an X-ray and getting a projection in one angle. When you rotate the gantry, you will acquire the thing in the middle, called the sinogram. Similar to MRI for sparse view CT, you will have subsampled sinogram, from which you will have to reconstruct the full image or the full sinogram. Now let us come back to the problem formulation. In the Bayesian perspective, as I said earlier, there are so many feasible X's that could produce the same Y. Hence, it would only make sense to specify the distribution of good X's rather than a single point estimate. Here, what you want is to perform posterior sampling. You want to sample from the distribution P of X given Y, where Y is given from the equation AX plus eta. When you're using a diffusion model to sample from the prior, we can simply discretize the reverse SDE, as I mentioned earlier from the generative process of the diffusion model, and solve this numerically, for example, by using Euler discretization proposed here. Well, what can you do when you want to sample from the posterior distribution? Well, one of the most straightforward ways is to perform iterative projections, where you perform an unconditional update and do projection to the measurement subspace. Notably, there is a theorem that states that given small enough step sizes, such iterative projections guarantee sampling from the posterior distribution. For cases in medical imaging, when we have linear measurements, it turns out that such data consistency projections are simple to perform and can be done in closed form without noticeable computational cost. Using this idea, I published a paper applying this method for compressed sensing MRI. The idea is simple. After training the score function with high-quality DICOM images, we can use the score function to perform MRI reconstruction by iterating denoising steps and data consistency steps. Here, both the predictor and the corrector corresponds to different types of denoising steps. In order to perform posterior sampling, we start from the usual Gaussian noise as in sampling from the prior, And for every iteration, we inject the information that we know about Y by performing projections onto the measurement subspace. Albeit the figure on the right is drawn for the case of CT, we can think in an analogous fashion in MRI as well. Using the intermediate sample xt hat, we first transform the image to the measurement domain. In the measurement domain, we replace the values in the indices that are known from Y with the values that we have already, and keep the values in the rest of the mask intact. This is a form of projection, and we iterate this process over and over again. One notable advantage of these methods is that they are agnostic to the form model. This is especially relevant for MRI measurements, as there are so many different subsampling schemes according to the circumstances. As we do not require any knowledge of the form model during the training process, during the training of the score function, or in other words, training of the diffusion model, it is agnostic to the form model and adapts to different measurements perfectly well. Notably, it achieves state-of-the-art performance and is particularly strong at capturing the high-frequency details, which can be attributed to the iterative refinement scheme of the diffusion models. Now, recall that I said we train the score function with DICOM images, meaning that the network has only seen magnitude images. However, we see amazing generalization capacity of these models. Namely, we can use the same model trained with DICOM images only to reconstruct complex valued image, and even multi-coil images separately, being applicable to practical measurements models, as in parallel imaging MRI. Moreover, again due to the generalization capacity, these models generalize well to unseen anatomies and contrasts. Here, the model was trained on proton density coronal knee scans only, yet is able to solve image reconstruction tasks of brain, or even in MSK images. Another intriguing property of these models is that since we are essentially sampling from the posterior distribution, every time the reconstruction will be at least slightly different. Due to this property, we can compute the uncertainty. Notice that the uncertainty measured with the pixel-wise standard deviation grows as the acceleration factor grows, which matches with our intuition. There must be more uncertainty if we have more and more sparse measurements. Now, in this case, we apply the same iterative projection scheme of diffusion models to the case of sparse view CT reconstruction. Here we see that even from very sparse measurements, such as 10 view, our method is able to reconstruct an image that is very close to the actual ground truth. Again, when we push it down to 5 view, we are still able to achieve decent reconstruction that closely matches the ground truth. Okay, now let's move on to another paper called Regularized Reverse Diffusion for Denoising, which is why this talk is happening in the first place. In this work, we tackle denoising problems arising in MRI measurements, another important subject in the area. Notably, denoising is a special case where the measurement operator is the identity function, and we only take into account the measurement noise of the system. Well, can we use diffusion models in this case? We answer with a positive, and the idea is hijacking the reverse SDE. Specifically assume that we know the noise level of the given noisy image. Then we can start the reverse diffusion process, starting from that noise level and run the reverse diffusion process thereon. Well, but is simply running reverse diffusion enough for denoising? The answer is no, because the process is generative and full of stochasticity. During the reverse diffusion process, important structures may change, which is the least thing that you want in medical imaging. This is when the regularization comes in. Empirically, for the case of denoising, we find that keeping the low frequency parts intact while only correcting the high frequency components works quite well in keeping the overall structure intact. This is similar to what we did in MRI reconstruction, but now the mask is focused on the low frequency parts. The second regularization that we impose is called manifold constraint gradients, which is hard to explain for now, but don't worry because we'll get back to this later on, as this is directly related to our second method on solving inverse problem with diffusion. In any event, let's visualize the results. These in vivo test images were acquired through caipirinha scans with reduced FOV and thin slice thickness to visualize small lesions, and therefore contains excessive noise and are typically of low resolution. When we apply our method here, together with an additional denoising part, also done through diffusion models, we acquire results shown in this figure, greatly improving the noisy, low SNR images shown on the right. This is in stark contrast to conventional self-supervised learning-based deep learning models presented in the left, where the methods are incapable of removing complex noise nor increase the resolution. Now, what kind of advantages do we have over conventional one-step denoising methods? First of all, similar to MRI reconstruction, we are endowed with the uncertainty estimation. Moreover, since we have an additional degree of freedom of where we actually start the reverse diffusion process, we can choose how much denoising that the user wants to perform. Okay, I think we did enough showing how option 1 of alternating projections work. Let's now dive into the second, more recent method of performing posterior sampling with diffusion. The idea is simple. From the prior sampling strategy with the score function, we can apply Bayes' theorem to achieve posterior sampling on the bottom. This is useful because for inverse problems, the likelihood P of y given x is typically known. For example, it can be Poisson or Gaussian so that we can plug it in. However, care must be taken because gradient of the log likelihood in this case is in fact intractable. Note that this is different from my claim earlier that the likelihood function is in most cases known. This arises from the fact that there are noisy xi's here rather than x0. Let us dive in to closely examine what I mean by this. To see why this is the case, consider the following probabilistic graph in the context of diffusion models. We know two conditional distributions, P of y given x0 and P of xt given x0. For my explanation, to be a bit more intuitive, I'm giving an example of inpainting here, where x is our clean image, y is the masked image, and xt would be the noised image from the clean image. Now, the first one is the measurement distribution. This is typically Gaussian. And the second distribution is the forward diffusion distribution, which is also Gaussian. However, the reverse distribution, P of x0 given xt, shown with blue dotted line here, is intractable in general. Hence, P of y given xt is intractable because we have no information about this blue dotted line. So in our work, we aim to approximate the intractable distribution. The first key comes from the factorization. Since x0 is conditionally independent on y and xt, we can factor the integrand as follows, where the former term is what we know, and the latter term is what we partially know. And by partially known, I mean that we know how to obtain the posterior mean of the distribution, which is given by the Tweedy's formula. While this may sound fancy, this is nothing but computing the denoised estimate with the predicted residual noise with the score function. It just happens to be that the equation matches with the classic Tweedy's formula, as you can see in the figure, as the predicted diffusion, the pre-trained diffusion model is very powerful. It is capable of predicting the denoised estimate, even when we have such very high noise. To fully enjoy the effectiveness of Tweedy's formula, and because leaving the expectation outside is intractable, let us push the expectation inside. When we do that, by the Tweedy's formula proposition, we have a fully tractable distribution where the condition is now given by x0 hat, the denoised estimate from xt. Now, while I will not go into the details of this rigorous bound, we can also derive a rigorous upper bound for the approximation gap that we proposed here, making the method theoretically plausible. Now, thanks to Theorem 1, we can achieve what we call diffusion posterior sampling, or DPS in short. Another name for this method is manifold constraint gradients, which I mentioned while I I was explaining the MRI denoising parts. And this is called MCG in short. Now we start with standard Bayes rule in the context of diffusion models. Then we can apply theorem 1 to get the approximation. Then we can approximate the former term with the pre-trained score function, the diffusion model. And the latter term simply depends on the measurements model. For example, Gaussian or Poisson. Note that these gradients can be computed as their functional forms are known. We see that for Gaussian, we are essentially performing gradient descent that minimizes the squared L2 norm of the residual. Whereas for Poisson measurements, we are minimizing the squared weighted norm of the residual. Also note that x0 hat is actually a function of xt, computed with the forward pass through the neural network. Hence, in order to compute this gradient, we need backpropagation. Let's visually inspect what the approximated likelihood term is computing. In the forward pass, we first achieve the 2D denoised estimate through the score function and compute the residual error between the simulated measurement and the real measurement y. The residual error value is then used to take the gradient with respect to xt, which can be computed with backpropagation through the score function. Note that the derived method always works when we can compute backpropagation, and this is the only condition. Hence, we can solve nonlinear inverse problems that are much beyond simple linear inverse problems. And here we list 2 additional cases that are applicable in our case. Case 2 considers phase retrieval, where the forward measurement model involves taking the Fourier modulus. Even further, we can take our forward model to be another neural network parameterized with phi, and we can use this in our framework as we can compute backpropagation through this neural network G. Now, incorporating ancestral sampling for DDPMs, we have our algorithm of DPS, where we can derive separate algorithms according to the measurements model at hand. Note that line 7 is where DPS takes place. And if we were to remove line 7, we would simply be sampling from the prior distribution by recovering the usual ancestral sampling steps of DDPMs. Hence, our algorithm is very simple to implement. Now, while these results are not in the context of biomedical imaging, as I said, these are all mathematically equivalent. So I'll show you some of the results that we can obtain through DPS. So since our method is not dependent on the measurements model, we can apply the same score function to various problems. For example, this is the result of applying our method to super resolution that are contaminated with Gaussian noise. We can apply the same method for noisy inpainting, noisy Gaussian deblurring, motion deblurring, and also some other more hard nonlinear inverse problems such as phase retrieval. And as I said, we can also use some forward measurement models that are obtained through a neural network. Again, coming back to the regularization methods in MRI denoising slide, recall that we also used MCG regularization here. We can see that all this regularization is doing is performing gradient descent steps to penalize drifting away from the 2D denoised estimate x0 hat. Since theoretically, for Gaussian noise, this x0 hat point would correspond to the Bayes optimal solution. So it's kind of penalizing moving too far away from this denoised estimate x0 hat at every iteration. Now, up until now, we discussed ways to perform 2D medical imaging reconstructions and enhancements. However, in real-world situation, it is of utmost importance that we are able to perform 3-dimensional reconstruction that is coherent. In the following section, we will dive into how we can perform 3D medical image reconstruction solely from 2D diffusion models. Now, by 3D inverse problem, we can think of the following 3 representative examples. On the left, we have limited angle CT, where we only have measurements in the limited green angles. Sparse view CT considers the case where we have very few projections at hand, for example, a 4-view CT. Finally, compressed sensing MRI of 3D volumes is also the case of 3-dimensional inverse problem. First, look at why this problem is even interesting in the first place. One should note that there is no representation for everybody that everybody uses for 3D data. For 2D images, we do have a consensus, namely using discretized matrices to represent images. For 3D, using voxels isn't so desirable in many use cases. It's just too memory inefficient and tends to be very heavy if we try to scale over a 128 cubed resolution. These are the main reasons that the computer vision folks like to use meshes, point clouds, or more recently, neural fields. However, using representations other than voxels are not feasible for medical imaging inverse problems when seeing the interior of the 3D volume is of absolute necessity. Well then, can we use 3D voxel diffusion? The answer is absolutely not, since the diffusion model is already computationally too heavy with 2D diffusion, and our tiny GPUs would not be able to handle such memory. So our proposal is to leave two-dimensional diffusion as is and try to incorporate lessons from the more classic literature. Specifically, we bring the total variation prior, which essentially states that natural medical images tend to have sparse gradients. In particular, we choose to impose TV only to the redundant Z direction. As for XY dimension, the diffusion prior pretty much covers it all. Apologies for the sloppy notation, but I think you get the point. Now, we can implement our idea as follows. First, we denoise each slice with 2D score functions in parallel. So the denoising is done independently for each slice. If we only use step 1 iteratively, we get slices that are independent of each other, such that when seen from the coronal or the sagittal slices, they are incoherent. Hence, in the second step, we aggregate the slices to form the volume and minimize the following subproblem, which imposes both the data consistency and the TV prior to the Z direction. The optimization can be performed effectively with, for example, ADMM or FISTA, the usual compressed sensing algorithms that people used to use when we were dealing with model-based iterative reconstructions. Now we can visualize our method as follows. Again, in the first step, denoising is performed independently across slices. ADMM TV sub-optimization scheme is imposed jointly. However, if we were to naively implement this approach, it would mean that we would have to run the ADMM steps per every iteration, which would be computationally infeasible, or at least very slow. Hence, we propose another strategy called variable sharing, in which we treat all the primal and dual variables of ADMM as global variables that are shared through the whole reverse diffusion process. This would mean that we are warm starting all the ADMM and CG steps in between, which will lead to much faster convergence with limited number of steps. So like I explained with the figure, we first denoise with the score function, and then we'll apply ADMM TV, but we will run a single sweep of ADMM with a single sweep of CG. You might think that there's no way this is going to converge, but it does, since we can slowly update the estimates during the reverse diffusion process. With the proposed method, we are able to achieve reconstructions from extremely limited number of views. In this case, I'm showing 8-view reconstruction of computed tomography obtained through some parallel imaging system. And we see that we achieve coherent results across the whole volume, achieving state-of-the-art results. Now, in the paper, we show that we can apply the same methodology to all the three representative problems arising in medical imaging, including sparse view tomography, limited angle tomography, and compressed sensing MRI. Another thing that I want to highlight is that, again, in CT reconstruction case, we see very high generalization capacity. What I mean by this is that we train our diffusion model or the score function with these in vivo CT scans, and we apply the same model to reconstruct this out of distribution phantoms that consist of these spheres, and our model shows great performance even in this highly out of distribution sample. And with that, I would like to wrap up my presentation. If you have any questions, feel free to ask.